Streaming and the recording. Right, so this is friction lecture number 2 for us. So in the previous session, we had discussed about the two types of friction, kinetic friction and static friction. And we had started to discuss about the factors that friction depends on, like the normal reaction or the normal contact force, and something called the coefficient of friction, which is a unitless or dimensionless coefficient, which depends on the nature of the surfaces which are in contact and between which friction is acting. So let's just take a recap of that whole portion again, and we will then take it further from there. I have sent the lecture notes on the previous two lecture notes are there on the foundation builder as well as foundation builder new groups. Yeah, it is there on foundation builder new also. Let me just check once more. Oh, sorry. Yeah. One. Okay. Right. I'm sending it, Hitanshu. I think I just missed sending the notes for this friction session 1, right, on foundation new. Yeah. So I'm sending it across now. Right. So I think for some reason the notes had got missed, whereas the video was sent. So now you have the notes also. So anyhow, let's go through a quick recap of the concept of friction. So what we had learned is that friction is a type of contact force, but unlike normal reaction, it acts tangentially or parallel to the plane of contact in such a way that it opposes slipping between two surfaces. So friction is defined as a contact force that acts tangentially. And by tangentially, we mean parallel to the surface of contact. That is parallel to the surface or plane of contact, such that it either prevents slipping, in which case it is called static friction, or opposes slipping when slipping is already taking place. So friction is going against slipping. In that case, it is called kinetic friction. So this is what we had learned in the last lecture. So the two types of friction here, static friction and kinetic friction. Let's quickly understand the difference between them. So generally we denote static friction in a free body diagram with the symbol small f with S. In general, small f stands for friction in a free body diagram, and S or K will be given as a subscript to denote whether it is static friction or kinetic friction. So static friction, what situation it acts in? It acts in a situation where if external forces have a tangential component, okay, which gives a tendency to slip, or it produces a tendency to slip. But however, the slipping is not occurring because the friction is able to balance this tangential force. Okay. So there's a tendency of slipping. However, the friction opposing, or you can say balancing, this tangential force prevents slipping, prevents the object from slipping against the surface. In that case, it is called, such friction is called static friction. Static friction. And we have the property of static friction that it is less than equal to the coefficient of static friction multiplied by normal reaction. So it can adjust its value according to the external tangential force to prevent slipping, but in such a way that the maximum value to which it can, oppose is the upper limit, or what we call the limiting friction. So this value mu s into n, this is called the limiting friction, or it is also called the maximum limit of static friction. So that depends on those two things, the coefficient of friction and the normal reaction. Whereas we have seen that kinetic friction acts in a situation where if there is slipping between two surfaces which are in contact, and of course are rough surfaces, not smooth surfaces, then kinetic friction, which we denote with Fk, acts tangentially to oppose the slipping. And unlike static friction, kinetic friction does not adjust itself according to the external force, but it takes a fixed value which is equal to mu k into n. So static friction is a variable amount of force which can go up to a maximum limit of mu s into n. Whereas kinetic friction, wherever there is slipping occurring, kinetic friction will be acting in such a way that its magnitude will be a fixed amount, and that is coefficient of kinetic friction mu k into normal reaction. Okay. So these are a couple of things that we had discussed in the previous lecture. Of course, the kinetic friction part we had come to towards the end. So you might want to revise this carefully once, go through this, then we'll discuss this with some examples and it will become clearer. Okay, so let's come to an example to understand this difference between static and friction, kinetic friction more clearly. So suppose we have again this familiar situation for us, which we've been seeing since last lecture, that on a horizontal rough surface, we have placed a block initially at rest. It's just placed on this surface. So now Suppose this surface has a coefficient of static friction given to us as 0.25 and a coefficient of kinetic friction as 0.20. Now, generally, I should tell you that the difference between static and kinetic friction will not be so large. Here you can see it's a 5% variation. Generally speaking, it will not be so large. Okay, just give me a moment, guys. Yeah, so coming back to this, so what I was saying, generally the difference between static and kinetic friction is not so large. If static friction coefficient will be 0.25, then kinetic friction coefficient will be closer to something like 0.24 or even closer like 0.248 or something. But here, for just the sake of the example, I'm taking the quite a big difference, a 5% difference between static and kinetic friction. One is 0.25 and the other is 0.20. Now, also given the mass of the block is suppose 100 or rather 10 kg, the weight is 100 newtons because we'll take G as 10 meters per second square. Now, the block is initially at rest. So first thing we'll do is we'll find out the maximum limit of static friction, or what we call the limiting static friction that can act on the block. So find the maximum limit of static friction that can act on the block. Now, just because it can act on the block doesn't mean that it will act on the blocks. For example, if I've just placed a block on the surface without applying any tangential force, then it does not have any tendency to slip. So there will not be any static friction acting on it. Okay. And the second part we will see, find the friction, okay, in newtons and acceleration in meters per second square, if any, when a force, a horizontal external force of F equal to 15 newtons acts on it, 20 newtons acts on it, 30 newtons acts on it, and 35 newtons acts on it. Okay. And then we'll come to a third part also for this question. So just understand the data of the question first, then we'll discuss more. So obviously the entire solution will be from free body diagram. So we'll draw the free body diagram for each of these parts. Yeah, so correct. Ruk said very good. The first part's answer is correct. Okay, so let's understand the free body diagram of the block. In the first part, when we are not applying any force, then what all forces will be acting on the block when there is no horizontal external force applied on it? You will see that there will be only two forces acting on it, and both of them will be vertical forces. They will be the forces of weight and normal reaction. So actually in the first part, there will not be any friction acting, but we can find out what is the maximum possible friction. If friction needs to act, then what is the maximum limit till which friction can act? Okay. So in this case, we can see that there is no external tangential force. That means no force which is acting parallel to the surface initially. Okay. So that means there is no tendency to slip. So if there's no tendency to slip, then friction does not act. Friction only comes into play when there's a tendency to slip. So this is very important to understand over here. There is, as long as there's no external tangential force, there is no tendency to slip. Okay. So that will mean that there is no friction which will act on it. Okay. However, we do know that the maximum available friction that can act, which we call the limiting friction, वो कितना होगा? That is the maximum value of static friction. That will be coefficient of static friction into normal reaction. So here we can see the normal reaction will be equal to the weight, which will be 100 newtons. Okay. And we already been told that the coefficient of static friction is 0.25. So from this we know that this is going to be 25 newtons. So up to 25 newtons of friction can act, but it will not be acting initially until and unless we apply some tangential force. Hope this point is clear to all of you, that initially there will not be any friction acting. Why? Because there is no tendency to slip. Only when I apply some force or give it some tendency to slip, then friction will come into play, which will happen in the second part. Okay, now let's take this further to the second part, when we are applying that force on it. So that is where knowing this limiting value will be handy from before, because now we know what to expect when we apply some external force. Okay. So in the second part, so even though it's not mentioned what is the direction of the force, we can just assume some direction as long as it's parallel to the surface or it's acting tangentially. And of course, it does not affect the vertical forces, because parallel to the surface here means horizontal. So now we are applying some kind of horizontal force or tangential to the surface. So let's assume the force is acting towards the right. So what will happen now? The moment we apply some force, okay, so when F is applied horizontally, okay, the block tends to slip. tends to slip because of this. So immediately friction comes into play. Friction acts such that one of the two things will happen. Now we can see that if the external force is less than equal to the maximum static friction, then what will happen? Then the block will remain at rest. Okay. So in other words, we can see here that F is less than equal to 25 newtons. If I apply a force of no more than 25 newtons, then the block will not move because static friction will prevent it from slipping. Will be able to balance this external force to prevent the block from slipping. Whereas on the other hand, if the force we apply is maximum static friction, okay, or F is greater than mu s into n, or in this case F is greater than 25 newtons, then what will happen? The block will start to slip. Because static friction will not be able to balance F. The F is too large for static friction to handle. Okay, and kinetic friction instead, Fk equal to mu k into n, will act opposing the slipping. So these are the two possibilities that can happen here. Now, for each of the parts that I've given you, we can figure out which of these possibilities is happening. Okay. So one type of friction or the other will definitely act. Now, which type of friction is acting, and therefore how much is the magnitude of friction, how much is the acceleration of the block in any, etc. That will all depend on the value of F. But in both cases, some kind of friction will act, either static or kinetic, depending on which of the two cases is occurring over here. Okay. So make a note of this section and now try out the different parts. So I had given you the different parts. F was either 15 newtons, or it was 20 newtons, or C part it was 30 newtons, or the D part it was 35 newtons. So each of these subparts now work out according to this information that we've written down here. So you'll find it easy to figure out which of the two situations is happening and work out the answer for each of these. So please try this out and send me the answers. You have to give me the acceleration and the friction acting for each of the parts A, B, C, and D. Okay, so just give me the friction and the acceleration in numerical value. The friction in newtons and the acceleration in meters per second square. Yes, very good, Kunj. All your answers are correct. Just check C and D, beta. The uh, the coefficient of kinetic friction is 0.2, no, not 0.02. Yes, Ruxa, your answers are correct. Kunj, check your C and D part. I think you've taken the coefficient of kinetic friction to be 0.02 by mistake. It should be 0.02, 0.20, not 0.02. Remember, the mass of the block is 10 kg. The coefficient of static friction is 0.25. The coefficient of kinetic friction is 0.20, not 0.02. All right. So ये जो kinetic friction का value होगा, this will be how much? This will be 20 newtons. So when there's kinetic friction acting, it will be 20 Newton force. Have you understood, Kunj? And Ruksar, what about the answers for the first two parts? Yes, that's correct now. Very good. Okay, so we can see that when we apply a force of 15 newtons, so what is happening? F is less than the maximum friction. Okay, so therefore the block will not slip. It will not slip. So the first thing we know immediately that the acceleration will be zero, and that static friction will be acting on it in such a way that F minus static friction should be zero. So the magnitude of friction acting should be equal to 15 newtons, and the acceleration of the block should be zero. For the case when we are applying an external force of 15 newtons. Okay. And of course, there is the vertical forces of mg, which is 100 newtons, and normal reaction, which is okay, so mg is equal to normal reaction equal to 100 newtons. This is the other thing. Now something very similar will happen in the B part, but only the value will be different, because now we are applying in the B part, the force we are applying is 20 newtons. Okay. But still the force is less than the maximum static friction. So still the block does not slip. So still there will be static friction, but the static friction now will have a different value. Its value will become 20 newtons instead of 15 newtons. The moment we increase this force from 15 to 20, automatically the amount of static friction acting will also increase. Okay, whereas the third case, or the C part, now the moment we apply a force of as much as 30 newtons, we can see now that F is becoming greater than maximum static friction. Okay, so the block slips. Okay, so when it slips, it will have a non-zero acceleration, and the friction acting on it will now instead be kinetic friction. So now we will have the equation that F minus kinetic friction is equal to Ma, and of course normal reaction balance is Mg, and kinetic friction is equal to mu k into normal reaction. So here the kinetic friction will be mu k into Mg, which is going to be 0.2 into 100, or 20 newtons. So the magnitude of the kinetic friction is going to be 20 newtons. So from equation 1, we can see that F minus mu k into Mg is equal to Ma. So 30 newtons minus 20 newtons will be the mass of the block into A. So that will tell me the acceleration is going to be 1 meter per second square. And kinetic friction of 20 newtons acts on the block. So this is how the situation changes between the part B and part C. The moment we apply a force more than the limiting friction, the slipping starts to occur. And when slipping starts to occur, the nature of friction changes from static friction to kinetic friction. So accordingly, the value of friction acting changes to mu k into normal reaction. It is not dependent on the coefficient of static friction anymore. Now it is dependent on the coefficient of kinetic friction. Yes, Rupesh, I'll scroll up. Just give me a second. We'll finish the last part of the question also. Or you know what? Let's review this first. Then we will come back to this. Okay. So come back to the general situation of second part. When we apply some force, it is either one of these two things that can happen. Either case one, this can happen, but for this, the condition is that F should be less than equal to 25 newtons. Or the case two can happen, but for this, the condition is that the F should be greater than 25 newtons. Okay. So now based on this, you can see which of these is happening in each of the parts. I've not done the D part yet, but you can see A, B, C. We can easily understand which of these two cases is occurring, case one or case two. Uday, very good. That's the correct answer for D part. Okay, so hope these individual parts A and B and C are clear now. And soon we'll move on to the part D, where the force we are applying is 35 newtons instead of 30. Just check the calculation of the last part. And the force is 35 newtons. Your value of friction is correct, but just check for the acceleration for the last part. Okay, so coming to part D now, somewhat similar to part C, but only the value of the force or the magnitude of this force is become even greater. So accordingly, the acceleration will also become even more. What we expect here, the acceleration will become even more, because kinetic friction, remember, does not change its value. Its value will remain mu k into n. So its value will remain 20 newtons. Okay. So in this B part, again, F is greater than maximum friction. So the block slips. Okay. So F minus kinetic friction is again equal to ma, but this time this is 35 newtons and this is going to remain 20 newtons. So the acceleration would have increased to 1.5 meters per second square now. Yes, that's correct, Home. Good. Okay. So the important thing here you can see is that between C and D, you're changing the external force from 30 to 35, but that does not affect the friction, because it is which type of friction? It is kinetic friction. Whereas between A and B, when you change the force from 15 to 20, the amount of friction acting also changed. Why? Because it was static friction. Static friction always adjusts itself in such a way. Okay, no problems. Okay. Uh, so you got the answer now. So anyway, so coming back to this, in the case of static friction, the value of static friction adjusts itself according to the external force. When it was 15, the static friction was 15. When we increase the force to 20, the static friction also increased to 20. But once the slipping has started, the friction cannot adjust itself according to external force. It has a fixed value of coefficient of kinetic friction into n, which in this case is 20 newtons. So whether we are applying a force of 30, 40, 50, whatever, but the moment the slipping is occurring, the friction has a fixed value, which is which is going to be 20 newtons in this case. Okay, so this was an important example to illustrate this point. Now let's see some more examples. So the concept of friction is going to be the same in every situation that we see, and we are always going to use the free body diagram to understand how much friction is available. So the critical thing in the free body diagram will be to understand normal reaction, and from that we can see whether or not slipping is occurring, because from the normal reaction we can get the values of the limiting friction and kinetic friction. So let's look at another example. So this time we have this kind of a situation. We have a tabletop which is rough with a pulley attached at the end like this. Okay, so this is a rough surface with a pulley fixed over here. And what we are doing is a light thread is going around the pulley attached to a system of two blocks like this. So this is the block A, let's say. This is the block B. And this is a rough surface. Now given to us that the coefficient of static friction on the rough surface this time is 0.5, and the coefficient of kinetic friction is 0.48, and the mass of the block A is equal to, let's say, 20 kilograms. Okay. So the first thing we'll understand here is find the maximum possible value of MB such that system may remain stationary after releasing the block B. If we release the block B, the system still remains stationary. So what is the maximum possible mass of B, MB? Okay. This we have to find. Second, find the friction on A, the tension in the thread Find the friction. Let's denote it with the symbol F acting on E. Tension capital T in the thread and acceleration of A and B. If mass of B is equal to 4 kilograms, mass of B is equal to 12 kilograms. Okay, take G as 10 meters per second square. So let's try out this question now. So you can see the weight of B is pulling it down, creating a tension in the thread and giving the tendency of the block A to slip towards the right. Because the moment you release B, the weight of that block will cause the string to develop tension, and the string developing tension means it's pulling the block A towards the right. So the block A will have a tendency of slipping towards the right, but it may or may not slip depending on how much tension the string has, because we have friction available to us in the surface. So the tension is more than a certain limit, then it cannot prevent, friction cannot prevent the slipping. Whereas if it's less than a certain limit, then the friction will be able to prevent slipping from occurring. That's what this question is about. So what you do is you make separate free body diagrams for A and B and find the condition for A and B to remain at rest. That will give you an idea of how to calculate the first part. So make individual free body diagrams for A and B, assuming that the system remains at rest after you release B. Yes, Ruksar, very good. The answer to first part is correct. Yes, Kunj, very good, correct. Okay, so we assume that kind of situation. Now within this only we can make the free body diagrams. So and on block A, there should be static friction because its acceleration is 0. And wait. Yes, very good, Kunj. Correct for the second part also. So for this first part only, for equilibrium, for the block A, you can see that tension has to be balanced by static friction, and normal reaction is equal to mg. So that is 200 newtons. So this is our first equation. Let's use this later. Okay, now you can also see that maximum static friction available is equal to mu s into n. So that is going to be 0.5 into 200. So the maximum static friction available to us is going to be 100 newtons. Now for the block B to remain in equilibrium, the weight of B has to be balanced by the tension. Okay. So solving equation 1 and 2, from comparison of equation 1 and 2, the weight of B has to be equal to the static friction. Okay. Now we use this concept that since static friction cannot exceed the maximum value, okay, so the weight of B should not exceed the maximum for equilibrium. That is, for the net force to be 0, this is the condition. So the weight of B should not exceed this thing. Okay. Or in other words, so the maximum possible mass of B for the equilibrium condition, for the situation where there is no slipping. Okay. And once we have calculated this limiting value of 10 kg, we can see how it will help us in solving the second part also. Because in second part, for the first section, for the A section, I've taken the mass of B to be 4 kg. So you can see it's less than 10 kg. So obviously this will be a situation where there is equilibrium or no slipping. So you can solve using the same free body diagram. Whereas for the B part, where we've taken the mass of B to be 12 kg, we can see that there will be slipping. Slipping occurs. So acceleration will not be 0. And the friction acting will be kinetic friction. Yes, Kunj, very good. Correct for the third part also, or for the B part of 2. Okay, so for the 4 kg case, you can just use the same set of free body diagrams. There's no difference at all. Okay. Whereas for the 12 kg part, you will have to adjust it with kinetic friction and the condition of slipping. So when we take the mass of B as 4 kg, you can see that there will be no slipping. Okay. So the tension will be equal to the weight of B, will be 40 newtons. Is one thing. Okay. And the static friction acting on E will balance the tension. So that will be 40 newtons. And the acceleration of the system will be 0. So these are my answers. Tension, friction, and the friction will be static in nature, and acceleration. Yes, Ruk said that is correct. Okay, Ayush, I'll just take you back to this for a minute. Note down whatever you need to. Okay. So now let's come back to the second part of the question. So initially when this mass is 4 kg, this is what is happening. Now let's see what happens when we take the mass to 12 kg instead. So now there will be a change in how the system behaves. The moment we take 12 kg, now A slips. Okay, so the acceleration will be non-zero, and the friction will be kinetic friction equal to mu k into weight of E. Okay. So we'll come to that. So we can see here that this block will have an acceleration like this. This block will have a downward acceleration of same magnitude. Okay, and this will be kinetic friction acting. So for the B, we will have weight minus tension is equal to mass into acceleration. So we'll have 120 minus T is equal to 12A. That's our first equation. And for the block A, we'll have T minus kinetic friction is equal to mass into acceleration. Now here, a normal reaction will be equal to weight. So that is 200 newtons. Okay. So we also know that kinetic friction will be equal to this. So it will be 0.48 into 200. So it will be 96 newtons. Okay. So now next we substitute the value of kinetic friction here. So this equation becomes T minus 96 is equal to 20A. This becomes our second equation. Okay. So now we just add equation 1 plus 2. So T will cancel out and we'll get 120 minus 96 is equal to 12 plus 20 E. So as you can see, this is 24 newtons is equal to 32 E. So this will be the acceleration. Okay. So this will be the magnitude of the acceleration, and the friction acting will be kinetic friction, which we've already calculated, of 96 newtons. And let's substitute this here to get the tension also. Tension, for example, from this equation is 96 plus 20e. So that is 96 plus 20 into 3 by 4. Okay, so the tension in the string will be 111. Is that correct? Yeah, seems correct. Okay, so friction, acceleration, and tension. These are the three values you are asked to calculate. Okay, people. So hope this question is clear to you. Yeah, Itanshu, whatever is required for this question is written down on the board. So go through it later. All the information about the question is given over here. Okay, and how to solve it and all the values and equations and everything I've explained on the board. So if you just go through it once more, you'll find whatever is required. Yeah, that's okay, no problem. Okay. So hope the equations are clear for all the three parts. Okay, very good. Now next, let's look at another question. So now the difference is this time, this block, which is stationary on the surface here, we are going to apply a force on it, but the force will be applied not horizontally. It will be a pulling force, which is at an angle theta like this. So the block is initially at rest. At t equal to 0, the initial velocity of the block is 0. And this has a coefficient of static friction equal to 0.6 and a coefficient of kinetic friction equal to 0.5. Okay. Now given that the mass of the block is 10 kgs, we'll take g equal to 10 meters per second square. Now an external force of F equal to, let's assume the force to be 100 newtons, acting at an angle of 37 degrees is applied. So find the acceleration, if any, the block. Next case, apply a force of 50 newtons. Actually, change the first part, make the first part 50 newtons at an angle of 37. Second part, we increase the force to force of 100 newtons at theta equal to 53 degrees instead. So again, find the acceleration for the block, if any. Okay, so try this question out. Now the hint to you is, okay, make the free body diagram and resolve F into horizontal and vertical components. Note that here normal reaction is not equal to mg because F's vertical component also acts. So it affects the value of normal reaction. So just take that as a hint while solving this question and try this out. No, Rukhsar, see, you have to understand that static friction tries to balance the tangential force. So it's not necessarily equal to mu n. It can be less than mu n also, no? So now you're giving the answer for the second part or the first part, Rukhsar? It's not correct. See, how much is F cos theta in the first part? The tangential component of force, the horizontal component, that F cos theta is how much? It is 40 newtons, right? Whereas how much is the normal reaction? It is mg minus F sin theta, no? So it's 70 newtons. Okay. So how much is the maximum static friction available to you? 0.6 into normal reaction. No? So you can see that the maximum static friction is more than the tangential force, is more than F cos theta. So it will be able to prevent slipping. Right. So what should be the acceleration in the first case? It should be 0. In the first case, you'll see that the maximum friction available to you will be about 42 newtons, maximum static friction. Whereas the tangential horizontal component of force is only 40 newtons. So it's a small margin, but it's less than the maximum static friction. Okay. So anyway, let's look at the free body diagram to work that out. Okay, so we are applying the force of 3 newtons at an angle of 37 degrees. Okay. And of course, the weight of the block, normal reaction, okay, and some kind of friction will be there. So we don't know whether this is static or kinetic yet. We'll work this out. Okay. So the mass of the block was 10 kg. So when we take components of the forces, we can see that this force will have a horizontal component of 40 newtons, a vertical component of 30 newtons. Okay. mg is 100 newtons. Okay. So therefore, normal reaction, we will find out next how much it becomes. So you can see that normal reaction will become mg minus f sine theta. So it will be 70 newtons. So from that we can also understand that maximum static friction, which is mu s into n, is 0.6 into 70. So it is newtons. You can now see something interesting, that the maximum friction is more than the amount of force which is trying to make it slip. So here we can also see that F cos theta, this is the tangential force, okay, which is trying to make the block slip. So this is the force that friction will oppose. Okay. Whereas the maximum friction available to us is 42. So that shows that F cos theta is less than maximum friction. Therefore, there is no slipping. Okay. So therefore, we now know that, okay, this friction acting here, it will be static friction. and the acceleration of this will be 0. Okay, so therefore we know that static friction equal to F cos theta. Okay. So static friction is equal to 40 newtons acts on the block, and the acceleration of the block is 0. Whereas n plus F sine theta, so the normal reaction was 70 newtons. So this is what is happening in the first case. Now in the second case, we are changing the values. Take F as 100 newtons and theta as 53 degrees and try to do the same type of calculation. Okay. So please go through this carefully and let me know if there's any doubt with the free body diagram or with the values. So using the standard values of sine 37 as 3 by 5 and cos 37 as 4 by 5. Very good, Om. Now work out the second part and try to get the answer correct, please, for the second part. Change the magnitude of the force from 50 to 100 and change the angle theta from 37 to 53, keeping everything else the same. Okay, I will verify the answer. Please send it to me. Coefficient of kinetic friction is 0.6. Huh? Sorry, 0.5. So you use all these values. Okay, I'm writing them again over here. The mass of the block is the same, 10 kg. Coefficient of static friction was 0.6. Coefficient of kinetic friction is 0.5. Yes, Kunj, your answer is correct. Very good. No, Hitanshu, check your answer for normal reaction first. Yes, that is correct, Om. Okay, so I'm telling you the answers. Just verify if you got it correct. You should be getting the acceleration as 5 meters per second square because you will get the normal reaction as 20 newtons. And therefore, kinetic friction of mu k into n or 10 newtons will be acting. Okay, now I'll show you why that all is happening. Just check if you're, yeah, good. Oh. So now this time we are applying a force like this of 100 newtons at an angle of 53 degrees. Okay. So when I make the free body diagram with these forces resolved and all shown, I'll be able to show that my components of the force F, the external force, are going to be F cos theta this time will become 60 newtons, and F sin theta will become 80 newtons. Then of course the weight of the body is 100 newtons downwards. So that shows me that the normal reaction is now going to be how much? It is going to be mg minus F sin theta. No? So the normal reaction is going to be only 20 newtons. Okay. So the first thing I can see is that n plus F sin theta is equal to mg. So this equation is showing me that n is equal to 20 newtons. So this now shows me that the maximum static friction available is 0.6 into 20. No? So it's only 12 newtons. Okay. So therefore I can see now that F cos theta is larger than maximum friction. So this is the situation where slipping will occur. So this tells me that the block will slip with a non-zero acceleration, and kinetic friction of mu k into n, that is 0.5 into 20, or kinetic friction of 10 newtons will act on it. So now I know that in this diagram the next thing I have to add is the frictional force, and that will be which type of friction? It will be kinetic friction. The body will therefore accelerate So this kinetic friction we've just seen will be 10 newtons in magnitude, because the normal reaction was 20 newtons. So we'll have the other equation for the block will be F cos theta minus kinetic friction is mass into acceleration. That will be our next equation. So F cos theta is 60, kinetic friction is 10. So you can see that the acceleration will be 5 meters per second square. This is the acceleration, this will be the frictional force acting, this is the normal reaction. So these are all the critical values that you require in this question. So whenever we are applying force at an angle like this, we have to be extra careful to calculate the limiting friction, because normal reaction is not going to be equal to weight. It is affected by the vertical component of the force. Okay, people, so let's move on to another situation of rough surfaces. This time we'll look at rough inclined surfaces or rough inclined planes. So next example, let's take the situation of a block placed on a rough inclined plane and released from rest. And let's find out the condition for it to slip versus not slip. Okay. So one thing, in many questions you will see that a single value of mu is given. If a single value of coefficient of friction is given, instead of static and kinetic friction separately, so that implies that the coefficient of static friction is equal to the coefficient of kinetic friction is equal to mu. Okay. So a block of mass m is placed on a rough inclined plane and released from rest. Okay. Find out its acceleration and the friction acting on it. If mass of the block is 5 kg, theta is 37 degrees, and the coefficient of friction is 0.5. On the second case, if the mass of the block is 6 kgs, theta is 30 degrees, and coefficient of friction is 0.6. Take g to be equal to 10 meters per second square. Okay. So let's try out this question next. So I will do the first part for you on the board, and then you can apply the similar method and check out the second part. So take down the data of the question first. Okay, so let's start with the first part. So whenever we have a block on an inclined surface, you know that to understand the normal reaction, we have to resolve the gravitational force into components like this. So if this angle is theta, then the gravitational force acting on it, which is vertically downwards, will always be such that it makes an angle of theta with the normal to the inclined plane. This is the normal to the inclined plane. The gravitational force will make that angle theta with it. Okay. Normal reaction will of course act perpendicular to the inclined planes, act like this. Okay. And in this case, whatever friction acts, whether it is static or kinetic, it will act like this. So this is friction. Now we don't know whether it is static or kinetic. We don't know whether the block is accelerating or not. So to begin with, this is your force diagram. So let's resolve the forces, taking this as our x-axis, the inclined surface is our x-axis, and the perpendicular to the incline as our y-axis. Okay. So let's begin by resolving the gravitational force. So we can see that this is the sine component, this is the cos component. So ultimately, the normal reaction will balance, okay, and the friction will be trying to oppose this. So what we can understand here is that mg sine theta, this is the tangential component of the weight. So this gives the block the tendency to slip. Okay. So friction opposes this. So that's one thing. Now the other thing we can understand directly from the free body diagram is that normal reaction is equal to mg cos theta. Okay. So therefore, maximum static friction is equal to mu s into mg cos theta. Now in this case, m was 5 kg and theta was 37 degrees. So the normal reaction was coming out to be 40 newtons, taking G as 10. And the coefficient of friction was 0.5. Okay. So the maximum static friction that we have was 0.5 into 40. So it was 20 newtons. So this is the maximum friction. Whereas this component is trying to create the slipping. This mg sine theta is how much in this case? It is 30 newtons. Yes, so the maximum friction we have is 20 newtons, whereas this is okay. So what we can see here is that therefore mg sine theta is exceeding the maximum friction. Okay, so that means the block will slip. So its acceleration will be non-zero, and the friction will be kinetic friction, which will be mu k into n. So in this case, that will be mu mg cos theta only, because the coefficient of kinetic friction is the same as the coefficient of static friction is equal to mu. Okay, so this free body diagram will now correspond to this situation that the block will be accelerating and the type of friction acting will be kinetic friction that we have confirmed from the values. So this will be kinetic friction, which will be mu k into n. So in this case, this will become 20 newtons. Okay, because this was 40, this was 30. Its normal reaction was 40. So that's how we got the maximum friction as 20. Okay, so we now know that straight down the inclined plane. So it will correspond to this free body diagram. And for this, we will have mg sine theta minus kinetic friction is mass into acceleration. Okay. Normal reaction is equal to mg cos theta. So second equation. And of course, the kinetic friction. So that is in this case mu mg cos theta. So solving this and substituting here, we will get mg sine theta, which was 30 newtons, minus kinetic friction, which is 20 newtons, will become mass into acceleration. So you can see the acceleration will be 2 meters per second square. And the friction, which will be kinetic friction, will be 20 newtons. So this much friction is acting, and this is the acceleration of the block in this particular case. Now just go through this very carefully and make sure you understand each and every step. Okay? Discuss with me anything that is required. And then we'll move on to the second part, where you can see the value has changed to 6 kgs. Okay, so this was the first part. Okay, now after this, you try to work out the second part yourself. Oi, get it out. Down. Down. Kitty. Okay, second case we will see. Yes, Kunj, very good. Your answer is correct. Okay. So let's use these values now. 6 kg mass and 30-degree angle, and coefficient of friction is 0.6. Let's see what happens here now. Okay. So we can see that this time the normal reaction will be equal to how much? It will be mg cos theta. So that will be 30√3 newtons. Right? Taking the values correctly, I hope. Yeah, 6 kg, 0.6 and whereas the tangential component of force or the tangential component of weight will be 30 newtons. Okay. So now let's try to find out what is the friction available to us. So we can see that normal reaction is equal to 30√3 and maximum static friction become mu mg cos theta, because there is a single value of coefficient of friction given. So that is working out to be how much now? It is 0.6 into 30√3. So it is 18√3. So it's 18 into 1.73. You want to really check out the value. Okay, so its approximate value here is going to be about 31.14 newtons. You can see that is definitely greater than 30 newtons. whether you calculate the exact value or not. So immediately you can see that mg sine theta is less than maximum static friction. So the block will not slip. Its acceleration will be 0 and static friction acts on it to balance mg sine theta. So coming back to the free body diagram, this will be static friction and the acceleration of the block will be 0. So now from this you can see that the second equation will now become like this, that static friction balances mg sine theta. So even though the maximum static friction is more than 31 newtons, but only 30 newtons of friction will act and the acceleration of the block will be 0. Okay. So because the coefficient of friction was different and the angle theta was different, here we are getting the condition that mg sine theta is less than, is less than the limiting friction. So it is the condition for equilibrium. Whereas in the previous case, mg sine theta was more than the limiting friction. So it was a case where slipping was occurring. Yeah, so 18 root 3 looks at it's okay, it's the correct value only. Okay, but you have to still check na कि 18 root 3 ज़्यादा बड़ा है कि mg sin theta ज़्यादा बड़ा है ना. So you still have to check that the numerical condition for that. Okay, so anyway, hope you understood this, Ruxan, and Om, you got the answer correct. Very good. Okay, so with that, people, we conclude today's session, and we will look at more problems based on friction in the next lecture, including the 2 block type of problems that you might have seen in H.C. Verma. So start doing questions from H.C. Verma friction chapter, and if anything is pending from the Newton's laws of motion chapter, try to finish it up. Next couple of lectures, we will be doing problems based on friction, but conceptually nothing new. We'll see how to apply in different types of situations with different free body diagrams, and that will wind up the chapter of friction. So please work accordingly on your assignments and exercise from the module, etc. That's it for today. Wish you all the best, people. The next chapter we will be doing will be work power energy. It is same chapter as in your NCRT or HC Verma or whatever. In between there's the chapter of circular motion, but that we have done in the other track of physics. So after friction, we'll be moving on to work power and energy. Okay, so bye people. Wish you all the best.